The equation in this example is xy prime plus quantity of 1 plus xy is equal to e to the negative x sine of 2x. Remember that our steps are to put the equation into standard form, find and use mu, integrate, and then isolate y. With that in mind, I'd like you to go ahead and pause this and work this out on your own. Well, how'd you do? Standard form, we got y prime plus the quantity of 1 plus x over x, y is equal to e to the negative x over x sine of 2x. Our mu, after all is said and done, turns out to be x e to the x using properties of exponents. And our left-hand side is the derivative with respect to x of x e to the xy. The right-hand side cleaned up really nicely. We just have sine of 2x. Integrating both sides just turns the right-hand side into negative 1/2 cosine 2x plus c. And then isolating y gives us y equals negative e to the negative x over 2x cosine 2x plus c e to the negative x over 2x. Of course, there are other forms of the answer, but as long as it's equivalent to this, then I'd say you're in good shape. And then we're still looking at interval of solution. We know x can't be 0, so we'll say the interval from 0 to infinity. And that assumption of positive x values is why I didn't need to use an absolute value in the natural log above. And finally, we see everything will go to 0 if x goes to infinity. So as it turns out, it's all transient. Now I've got another one I'd like you to try. dp dt plus 2tp equals p plus 4t minus 2. That's a mouthful. Here we have that p is the dependent variable and t is the independent variable. So we want our form to be dp dt plus, I'm just going to put it here as like q of t, because if I use p it's just confusing, times p is equal to, I'll say g of t over here on the right. So you're shooting for this form so you can identify what goes into the integrating factor and then proceed as before. Pause it, come back, see how you did. Standard form looks like dp dt plus the quantity of 2t minus 1p is equal to 4t minus 2. That gives us a mu of e to the t squared minus t. Multiplying that on both sides lets us write the left-hand side as a derivative of the product, and the right-hand side 4t minus 2 times e to the t squared minus t. Integrating using the substitution rule, I'm going to identify u is equal to t squared minus t, so du is 2t minus 1 dt, and we see we're just off by a factor of 2. So e to the t squared minus tp is equal to 2e to the t squared minus t plus c, and finally isolating p is going to give me p equals 2 plus ce to the t minus t squared. I went ahead and reversed the order of that because we divided, the exponent goes negative, you know how that goes. The interval of solution is negative infinity to infinity because there are no restrictions on t either in the solution or in any of the steps that we produced here. And the term ce to the t minus t squared is going to go to 0 if t goes to infinity, so that's our transient term. Next up we have quantity of x squared minus 1 dy dx plus 2y is equal to x plus 1 the quantity squared. Let's work on this together because of a couple of things that are going to pop up. Putting this into standard form, we have dy dx plus 2 over x squared minus 1y is equal to, we're going to end up with x plus 1 over x minus 1 because x plus 1, the quantity squared, factors x squared minus 1 factors, and we divide out one factor of x plus 1. Mu is then going to be e to the integral of 2 over x squared minus 1 dx, and I want to talk about that integral for just a moment. The integral of 2 over x squared minus 1 dx is something you might remember from second semester calculus, and it requires partial fraction decomposition. So we've got 2 over x plus 1, x minus 1 is equal to a over x plus 1 plus b over x minus 1. Remember, if we can factor a denominator of a proper fraction, then we set up multiple fractions, each one of which has one factor from the denominator. And in this case, the factors in the denominator, x plus 1 and x minus 1, are linear. Therefore, we're going to write down constant numerators. Clearing all the fractions in the equation allows us to write down that 2 is equal to a times the quantity of x minus 1 plus b times the quantity of x plus 1. Partial fraction decomposition is going to show up multiple times throughout this course. So if you need to, go back and refresh yourself. For now, I'm going to say, if we let x equal -1, we're going to zero out the b term, and we'll find that a is equal to -1. If we then let x equal 1, we're going to zero out the a term, and we'll find that b is equal to 1. Mu then becomes e to the integral of, and I'm going to write down b over x minus 1 first, because a is negative. So we've got 1 over x minus 1 minus 1 over x plus 1 dx. Integrating that is going to give us natural logs, right? So we've got e to the natural log of x minus 1 minus the natural log of x plus 1. I guess technically all those arguments need to be in absolute values. And then using properties of logs, we can say mu is equal to e to the natural log of the absolute value of x minus 1 over x plus 1, which means mu is equal to this x minus 1 over x plus 1, playing the same game with the absolute values that I've been playing when they come up. Now we've got the left-hand side as the derivative with respect to x, of x minus 1 over x plus 1 times y is equal to, well, that right-hand side is going to clean up nicely. It had been x plus 1 over x minus 1, so here we end up with simply 1. So x minus 1 over x plus 1 times y is x plus c, and y is equal to x squared plus x over x minus 1 plus c times the fraction x plus 1 over x minus 1. The interval of solution, I'm going to pick 1 to infinity. You could say it's infinity to -1 or -1 to 1. There are some restrictions here because we ended up dividing by x squared minus 1. But I'm going for the biggest interval of solution. And there are no transient terms.